Welcome to Fundamentals of Artificial Intelligence. We continue our discussion on planning. In the last lecture, we had introduced the idea of a planning agent. We saw how planning can be viewed as a type of problem solving in which the agent uses beliefs about actions and their consequences to arrive at a solution. We had introduced situation calculus, a variant of first order logic in which beliefs about the changing world can be represented. Situation calculus enables a knowledge based agent to reason about actions and thus look at the consequences of actions to finally arrive at a plan. We have looked at strips, a representation of the situation calculus for planning. In strips, every action can be seen as an operator that syntactically changes the world model, and using such a representation, we are in a position to arrive at a plan using what is called goal stack planning. The idea in goal stack planning is to push the sub goals and the actions into a stack and pick an action only when all its preconditions are satisfied. Recall that in the last lecture, we had walked through a blocks world problem in strips, and we saw how each of the sub goals and the actions were on a stack, and planning was about picking an action as its preconditions were being satisfied. The planning algorithm, referred to as goal stack planning, works with state descriptions, which are always consistent for growing plans, and goal descriptions for growing the search tree. One needs to realize that goal stack planning is incomplete, in the sense that it could terminate without finding a plan. Now, goal stack planning could commit to a wrong action at some time, and thereby it could reach a state from which a plan cannot be found. Goal stack planning, as already discussed in the previous lecture, breaks up a set of goal predicates into individual sub goals and then attempts to solve them one after another. Now, when these sub goals are being encountered, they come one after another in a sequence, and therefore the approach is also called linear planning. Linear planning, for the sub goals are attempted and solved in a linear order. Now, this may not be always possible, as we saw in the blocks world problem, where it may not be possible to break the main goal into two sub goals, which we refer to as the Sussman anomaly. Also, many of the planners in the real world would love to act not in sequence, but operate in parallel. So, we today look at another idea of planning, which is referred to as the plan space planning. Plan space planning works with plan structures. That is, you start with a plan and modify it to arrive at the final plan. Plan space planning is also referred to as nonlinear planning, for you can take any part of the plan and may change it to arrive at a goal. For example, let us say you had made a plan to get some medicine that would require that you go to a pharmacy. On the way, you could then decide to bring some fruit as well. This would need that you would move from the pharmacy to a fruit shop next door. Now, here the plan space approach, as you can see, does not constrain one to focus on only one sub goal continuously, and one can shift attention midway and in the process often solve problems like the Sussman anomaly correctly. The planning approach that we have described so far actually had risen with states, and the planner is looking at a state and a goal. If the state satisfies the goal, we have got a plan and the planner terminates. Or else it makes a search move over the state space looking for actions to add to the plan. On the contrary, in plan space planning, the idea is to consider the space of all possible plans and searches over the space for a plan. Now, algorithms in this category represent a plan as actions arranged in a partial order, and hence these are also referred to as partial order plans. Take the example of you getting ready in the morning to go out and you have to put on your shoes. Now, you have to put the left shoe as well as the right shoe. Whether putting the left shoe comes first or putting the right shoe comes first doesn't matter, and therefore the only thing that matters is that the final state, I should have the left shoe on and the right shoe on. These type of plans are called partial order plans. For here, the left socks and the left shoe has an order fixed, the right socks and the right shoe has an order fixed. If now I bring in a third step, which is about the right socks to be added to the plan, now we only want to make sure that putting on the right socks comes before putting on the right shoe. We do not care where they come with respect to the left shoe. Now, such planners, when they use the idea of putting these steps, they use the principle of least commitment. The least commitment principle states that one should only make choices about things that you currently care about, leaving the other choices to be worked out later. Now, this is a good idea, because making a choice about something you don't care about now, you are likely to make the wrong choice and have to backtrack later. So, instead of making a lot of backtracks, it would be best to commit to the least things now. A planner that can represent plans in which some steps are ordered with respect to each other and other steps are unordered is called a partial order planner. The alternative is a total order planner in which plans consist of a simple list of steps. Like example of putting on the shoes, I put the left socks, then I put the left shoe, I put the right socks and then I put the right shoe. Here the only sequence that's to be maintained is that the left socks has to be put before the left shoe and the right socks need to be put before the right shoe. I can in a sense put the left socks and the right socks, thereafter put the right shoe and then the left shoe. So, a partial order plan allows one to have steps which are unordered in a sense, and only some steps are ordered. A total order plan is about a simple list of steps, and now we can see that a totally ordered plan that is derived from a plan P by adding ordering constraints is called a linearization of P. So, let us come back to that example of putting the left shoe and the right shoe. Now, as we were discussing, I could put the left socks and then the right socks, or I need to put the left socks and the left shoe. So, the only ordering that is required is the left socks and the left shoe and the right socks and the right shoe. Given this partial order plan to me, I could think of generating a number of total order plans. Like here on your right is another plan where I start with the right socks, put the right shoe, then the left socks, then the left shoe, and finish putting on the shoes. A little consideration will show that I can have the following 6 total order plans out of the partial order plan of putting the left shoe and the right shoe. I could put the right socks, the left socks, the right shoe, the left shoe, or I could do the right socks, left socks, and then put the left shoe and then the right shoe, because the only ordering that I need to maintain is about the socks and the shoe. These 6 total order plans that are possible to be obtained from the partial order plan on the left of the screen are called linearizations of this plan P. Now, planners, even if I have not shown it in the total order or the partial order plans that I have shown in the previous slide, have to commit to bindings for variables in operators. For example, suppose our goal is to have milk and you have an action to buy an item from a store. Now, a sensible commitment for instantiation is to choose this action with the variable item bound to milk, because my goal is to have milk. Therefore, it is sensible to bind the item to milk. But then there is no good reason to pick up a binding for store. This is what the principle of least commitment says. I would leave store unbound and make the choice later. Now, one should realize that when I am delaying the commitment to a particular store, I am in a sense allowing the planner to make a good choice later. And using some strategy, I may be able to also prune out bad plans. Now, suppose for some reason, let us say the branch that includes the partially instantiated action of buying milk from a particular store would lead to a failure. Now, if we had committed to a store as well, then my search algorithm would force me to backtrack and consider another search. Keeping myself least committed and only committing to the item of milk, keeping the store unbound, would not generate this possibility. Now, a fully instantiated plan is one in which every variable is bound to a constant. Plans in which every variable is bound to a constant are called fully instantiated plans. We are now in a position to define what are the components of a plan in more formal terms. A plan has 4 components. 1, a set of actions where each action is one of the operators for the problem. Thereafter, there are a set of ordering constraints, A before B. But then this before does not mean necessarily immediately before B, and one needs to be very careful when dealing with these ordering constraints to avoid cycles. The third component of a plan is a set of causal links. Causal links are also referred to as protection intervals between actions. A to B over P read as A achieves P for B means that P must remain true from the time A is applied to the time B is applied. Now, for the example that we have been talking of about putting on the socks and the shoes, right socks and the right shoe, when I am talking of these two scenarios, then right socks on should remain true for me to go from right socks to right shoe. The fourth component of a plan is a set of open preconditions. The idea is to reduce the set of open preconditions to the empty set without introducing contradictions to arrive at a plan. Now, the initial plan, even before any refinements have taken place, is one which simply describes the unsolved problem. In essence, it just contains two steps: the start and the finish, with the start before the finish. Both the start and the finish have null accents associated with them. So, when it is time to execute the plan, they are ignored. The start step has no preconditions. All it specifies is its effect, and the effects add all the propositions that are true in the initial state. On the other hand, finish has the goal state as its precondition and does not have any effects. By defining a problem this way, in terms of just the start and the finish, the planner can start with the initial plan and manipulate it until they come up with a plan that is a solution. Now, a solution for a planning problem is a plan that an agent can execute and one that guarantees achievement of the goal. Consider a scenario in which we wanted to really make it easy to check that a plan is a solution. In that case, we could insist that only fully instantiated, totally ordered plans can be solutions. But one needs to understand that such a scenario is unsatisfactory for three reasons. One, it is natural for a planner to return a partial order plan than to arbitrarily choose one of the many linearizations of it. Like in the example of putting on the shoes, I had 6 linearizations out of the partial order plan. It is natural for a planner to return the partial order plan rather than to commit to one of the 6 linearizations. Second, many agents are capable of performing actions in parallel, and therefore it makes sense to allow solutions with parallel actions rather than just a sequence of steps. Lastly, when you are creating plans that may be combined with other plans to solve larger problems, one needs to retain the flexibility afforded by the partial ordering of actions. And therefore, when we are looking for a solution to a planning problem, a solution is a plan that is not fully instantiated or not a totally ordered plan. We want the solutions to be partially ordered, and we use a very simple definition saying that such a partially ordered plan will be solution when it is complete and consistent. Now, let us look at what we mean by complete and consistent plan. A complete plan is one in which every precondition of every step is achieved by some other step. A consistent plan is one in which there are no cycles in the ordering constraints and therefore no conflicts with the causal links. Now, if I have a consistent plan with no open preconditions, then I call it a solution or the plan that I am looking for. Let us take an illustrative example to understand this idea. Consider the robot needs to solve the following. It needs to get a quart of milk, a dark chocolate, and a good book. How does the robot go about solving this? Now, as discussed, we should note that we will start with just two states, one the start, the other the finish. So, at start, the robot is at home. There is a store that sells milk. There is another store that sells books, which we call the bookstore, and the store that we have sells milks and chocolates. Now, the goal for the robot is to have milk, have chocolate, have a book, and be at home. Now, a little reasoning will let you see that to start with, the robot is at home. To get these things, it must go from home to the store, collect these items, and somehow finally return back home to satisfy my end conditions. So, how do we plan this whole thing in a partial order plan? So, we start with a start state and a finish. The planner has an initial plan representing the start and the finish steps, and now on every iteration I would add one or more step. If it leads to an inconsistent plan, it would backtrack and try another branch of the search space. In order to keep the search focus, the planner would only add steps that serves to achieve the precondition that has not yet been achieved, and the causal links are used to keep track of this. So, as you see, the first condition not satisfied is having milk, and therefore, the first step would be an addition of an action of buying X. Now, any step about buying X, there would be a set of preconditions and a set of effects. If you are buying X, you must be at the store and the store must be selling X. Now, after you have done this action, you would have X. So, looking at this, you would love to add the step of buying milk here in your plan of things. Now, you would see that the preconditions are that you must be at the store and the store must be selling milk. If you look back here in the start state that we have put the conditions, we do have that the store sells milk, but we are at home. So, somewhere down the line we should have another action between buying milk and the start, which will take me from home to the store. We will come back to this in a little while, but first we are satisfying one condition of having milk by introducing an action of buying X. The next is about this simple establishment. Now, we say that a link is established if it represents a commitment on the part of an action to support the precondition for the next action. So, here there is a simple establishment of buying milk because it supports the precondition of have milk for my finished state. Similarly, we could add simple establishments of getting a chocolate and another simple establishment of getting the book. Now, one needs to realize at this point that getting the chocolate and the milk was about being at the store, whereas getting the book was about being at the bookstore. So, we have three links here of actions: buy milk, buy chocolate and buy book that we have added. Now, in order to satisfy that I am at the store, I would need to extend the plan by choosing two go actions. One that gets me to the store and another that gets me to the bookstore. So, I have another step addition of go there. So, the precondition is that I must be here, and the effect of that go there action is that I am there, but I am no longer here. So, not of at here. This I introduce in between my start and at store. So, I have this action here, go store, being introduced, and the precondition would be that I am at home and its effect would be that I am at store. I could be at the store for a chocolate or for milk, and I introduce here another go action which is about go to the bookstore, whose effect is that I am at the bookstore. Now, we have arrived at a very interesting scenario now. If go bookstore step goes first, then it will delete the at home, thereby clobbering the precondition required for the go store. Now, that is called a threat. So, this idea of threat or clobbering is a potentially intervening step that destroys the condition achieved by a clausal link. Like if I say go home, then it clobbers at supermarket. So, in order to avoid that threat, I can either do a demotion, that is put before go supermarket, or I could do a promotion, put after buy milk, the idea of going home. So, declobbering is that I have to do for removing the threat. Now, a threat, as I have seen it in the original planning example that I am talking of, is a step that deletes or clobbers a needed effect. So, S2 requires an effect of S1, that is, there is a clausal relation between S1 and S2, but the effect of S3 is to undo the effect S2 requires. So, then we say that it is a threat. Now, S3 therefore cannot occur between S1 and S2. It must either be before S1, in which case I say I have promoted S3, or it could be after S2, in which case I say I have done a demotion. Let us get back to that illustrative example, and now we could see that the go store and the go bookstore, they are clobbering each other. So, I could remove the threat by going home after going to the store and then going to the bookstore, but we would do something different. So, after visiting the store, if you could visit the bookstore, then this idea of at home being clobbered by bookstore will not be there. So, this is what I would do. So, basically the threat would be fixed by a demotion. I would add an ordering that I should buy the milk and thereafter go to the bookstore, and demotion would be brought in. So, an ordering would be made between S2 and S3. Another demotion is needed between buying the chocolate and going to the bookstore. So, that is what is added. Now, once I am at the bookstore, after getting the milk and the chocolate, I can buy the book, but then it would require that I return back home. So that would mean that I would have to add a go home action here at the bookstore. Now, that open precondition that I am at home and adding the action go home also causes a threat, because if you are at the bookstore and if you go home from there, then you would not be at the bookstore any longer to buy the book. So I have to introduce this demotion. So there are a couple of demotions that are introduced that are very important to realize. I will buy milk and then I have to be sure that then only I go to the bookstore, or buy chocolate and then only go to the bookstore. So these two, and the third one, which is about buying the book and then only going to this state about going home. So here is the final plan. I go to the store, buy milk and chocolate, go to the bookstore, buy the book and go home. Now, if you look at this final partial order plan, it can take a problem that would require many thousands of search states for a problem solving approach and solve it with only a few search states, because of the fact that I had done a least commitment nature of planning, meaning it only needs to search at all places where sub-plans interact with each other, and the causal links allow the planner to recognize when to abandon a doomed plan. Let us quickly recall our discussion of the Sussman anomaly from the blocks world problem. Now, having looked at a plan generated using a partial order planning algorithm, it would be nice to see if we could solve the Sussman anomaly in a similar manner. Now, quickly recalling the Sussman anomaly, here is my initial state where I have C on A and B on the table, and I want A on B and B on C. Now, any non-interleaved planner would typically separate the goal into sub-goals. That is, I would have A on B and B on C. If I am talking of pursuing the first goal, then the basic step is to move C out of the way and put A on top of B. While this sequence accomplishes goal 1, now the agent would have no option but to undo this step in order to achieve goal 2. Now, in a similar manner, if instead the planner starts with goal 2, then the most efficient solution is to move B onto C. But in order to achieve goal 1 now, it has to undo this path. So, on AB is undone to clear B when solving B on C, as can be seen here, and similarly on BC is undone to clear C when solving A on B. So, if you begin work on AB by clearing A, that is putting C on the table, then achieve on BC by stacking B on C, and achieve on AB by stacking A on B, then we could achieve the final result. But we can't do this using a stack within strips. Interleaving is required. So, non-interleaving planners where either all the steps for achieving G1 occur before G2 or all the steps for achieving G1 occur after G2 can't solve the Sussman anomaly. If I am in a position to intermix the order of the sub-goals or what are called interleaving planners, I can solve the Sussman anomaly, and the partial order planner is one planner that can solve the Sussman anomaly. So let's look at that. We have the initial state here where B is on the table and C is on A. We have the final state where I have B on C and A on B with C on the table. Let me take help of just two actions. One, which is stacking X on Y. Under a scenario where X needs to be clear and X needs to be on some Z and Y needs to be clear. So these are its preconditions. Under such a scenario, I can stack X on Y. Once I have X on Y, X would not be on Z and Y would not be clear, whereas Z would be clear, and stacking X on Y would finally give me X on Y. Similarly, I have another action which is about putting X on the table. The preconditions are that X must be clear, there must not be anything on top of X, and X must be over some Z. So if I am putting X on the table, then X is no longer on Z and the final result is that X is on the table. Now let us get our start and finish states. So finally it must be that A is on B and B is on C. To start with, I have C on A on the table, nothing on top of C, B on the table and nothing on top of B. So the first action that I take is about stacking B on C. Now the preconditions, B must be clear, B must be on some Z, and these conditions are clearly visible here. So I could have, this would be a C, clear C. So I could clearly have a stack operation happening. Similarly, I could think of having stack AB where A on Z and B is clear, so I could do stack AB. But then you need to realize that the stack AB clobbers the clear B here. So there is a threat to stack BC, and therefore I can solve this by putting after BC, and then I put on the table the block C, that operation which solves this precondition about clear A. And now this one you could see is again causing a threat, and that I must solve by put on table C before stack BC. So here is our final plan, which is about first putting C on the table, then putting B on C, and then finally putting A on B. So we saw that a partial order planar can solve the Sussman anomaly very easily. So to summarize, we have looked at planing agents which search to find a sequence of actions to achieve a goal. Now they have used a very flexible representation of states, operators, goals and plans, and we have looked at the strips representation which describes actions in terms of their preconditions and effects. Now it isn't feasible to search through the entire space as was done with problem solving search agents. So regression planning focuses the search. Strips assume sub goals are independent, and we could do what is called the goal stake planning. Partial order planners uses the principle of least commitment, and we have seen how declubbering or threat removal is used to arrive at the plan. Given the fact that even the simplest of planning problems are hard, we need methods to speed up search, and this is what we would take up in our final lecture on planning, where we will see some relaxation to the constraints that we have posed to the planning problems here, and also use some heuristic information to do planning. Thank you.